So here's a model I have for you. On the left is my model of the economy. Yeah, okay, it's pretty small. There's a capital stock, which represents all kinds of things, and that generates economic activity, and some of that economic activity helps the capital stock to grow. So that's my model of the economy, and as you can tell, that's not the part I'm worried about. Economic activity has some carbon intensity to it. You know, we're using petroleum and other coal. So economic activity tends to produce CO2. And CO2 produced tends to accumulate in the atmosphere. It actually accumulates differently in the lower and upper atmospheres, but I got one stock. And then I've got uptake of atmospheric, they call that sequestration, actually, but I'll just use uptake. In other words, it gets pulled out of the atmosphere. And CO2, as we have been repeatedly told by the world, is a heat-trapping gas. So there's an influence from atmospheric CO2, it should be from the concentration, down to outgoing global heat energy. What would be the sign on that arrow? The more atmospheric CO2 I've got, what happens to outgoing heat energy? It goes down because it's a heat-trapping gas. So there's a minus sign on that. Now, I'm going to ask for, we're going to do a thought experiment. I'm going to imagine that through some magic, not by shutting down the economy, but probably by shutting down its capital intensity, sending it to zero. That's my thought experiment. So we will simply stop producing CO2 from economic activity. Now, we're going to carry this thought experiment all the way through. What I'm really interested in is what happens to global heat energy, because that's where temperature comes from. And the conclusion we're going to get there ought to surprise you. All right, so production goes to zero. Atmospheric CO2 is like water in a tub. The inflow has stopped. The outflow is the drain. It's still going on. So what does atmospheric CO2 do? It starts to drop, and right away, right? The minute I've gone to zero, it starts to drop. So that little corner occurs at the same time. Cool. So right at that moment, what happens to outgoing global heat energy? Well, it's now atmospheric CO2 has started to go down, so that means that heat energy can start to leave, and so it's going to start curving up, and that little curve occurs at the same place. Now this part's a little bit hard. You have to think like a kid in a bathtub. I want to know whether global heat energy is going up or down. It's going up if the inflow is greater than the outflow, if the faucet's turned on more than the drain. It's going down if the inflow's less than the outflow, right? This is just a tub, it's just a faucet. And if the inflow is the same as the outflow, then it's not changing at all, right? So in order to know what's happening to global heat energy, we have to know what's happening to incoming solar heat energy. But that's been constant. That hasn't been doing anything, roughly. But is it higher or lower than outgoing global heat energy? What's been happening to global temperature? It's been going up. So that means incoming solar heat energy has been greater than outgoing, right? So if I moved it over there so you could see it, it would look like that. I just slid it over. See the crossing point? So where incoming is greater than outgoing, global heat energy is going up. Where incoming is less than outgoing, then the heat energy is going to start going down. So the graph of heat energy looks like that. And the peak there is where those two little curves on outgoing global heat energy cross. Before that, it was rising. At the cross, it's an equilibrium. And beyond the crossing point, it is starting down. And notice what has to be true. That corner has to be later than when we shut down CO2. It has to be later. And if you ask anybody that you know about it, if we shut down CO2 production today, what would happen to global heat energy? What would happen to global temperature? They'd say, man, it would start going down. And it would start going down right away, and it cannot because of the simple bathtub physics of stocks and flows. And an 8th grader can understand this.